Let's dive right into this explainer. Today, we're unpacking a truly fascinating agricultural thesis by Ismael Ramirez Moreno from the Instituto Tecnológico de Tlajomulco. And listen, this isn't just some dry academic exercise. It's a deep dive into an idea that could fundamentally revolutionize how we grow food in our cities, entirely off the grid. We're going to explore the science of optimizing a completely passive hydroponic system.
So ask yourself this ultimate urban farming question. Is it really possible to grow food at scale without any soil and without a single drop of electricity? I mean, we are so used to modern hydroponics being these high-tech, energy-hungry operations, right? You've got buzzing water pumps, timed aerators, complex circulation systems, the whole shebang. But what if we could just strip all of that away? What if we could create a highly productive, self-sustaining agricultural ecosystem that requires absolutely zero electrical power? The stakes here are incredibly high. And those stakes are driven by a very real, very pressing timeline. Let's rewind just a bit to 2023. This research was heavily motivated by the escalating global water and climate crises, specifically documented in regions like Jalisco, Mexico, throughout that year. Traditional agriculture is facing unprecedented challenges with water scarcity and totally unpredictable climates. There is this massive, urgent need to find sustainable, low-cost alternatives that just don't rely on fragile energy grids or abundant freshwater supplies. We need solutions that are truly resilient.
Enter our slightly flawed hero, the Kratky method. Developed back in the 1990s by Dr. Bernard Kratky, this is a beautifully simple, passive hydroponic technique. Here's how it works. You place a plant in a suspended net pot over a container of nutrient-rich water. No pumps, literally zero electricity. As the plant drinks, the water level slowly drops. And this reveals the absolute genius of the system. As that water level falls, it exposes the upper roots to the air, creating a natural air chamber. So the top roots breathe oxygen, while the bottom roots continue to drink the water and nutrients. It's an elegant, self-watering ecosystem.
But as with any hero, there's a fatal flaw. While the Kratky system boasts unbeatable benefits, like zero electricity, incredibly low cost, and a pretty foolproof setup, it faces microscopic biological villains. Because the water's completely static and unmoving, the oxygen in the liquid eventually just runs out. This leads to root hypoxia, which is exactly what it sounds like, literally suffocating those lower roots. Plus, without any circulation, the chemical makeup of that stagnant water becomes totally unstable. It alters the pH and basically locks away vital nutrients so the plant can't even get to them.
Section 1. The contestants. 3 innovative additives. To figure out how to fix a passive system without adding any active electrical components, Ramirez Moreno basically framed his experiment as a high-stakes biological battle. He set up this incredibly rigorous test using 60 basil plants over 6 weeks. He divided them into 5 distinct treatments. Treatment 1 used a mineral called zeolite soaked in a standard nutrient mix called Steiner Universal. Treatment 2 used zeolite but with a modified 10% ammonium mix. Treatment 3 mixed zeolite with a biological compost tea. Treatment 4 introduced a live, submerged aquatic plant, the foxtail plant. And finally, treatment 5 was our control, just the standard, unmodified Kratky system.
Okay, before we get to the results, I want to quickly explain one of our key players, zeolite clinoptilolite. Try to think of this not just as a microporous volcanic rock, but as a dynamic sponge. At a microscopic level, zeolite has this incredible three-dimensional cage-like structure that naturally traps and holds on to positively charged ions, stuff like calcium, potassium, and ammonium. Because of this high cation exchange capacity, it can actually store nutrients and buffer the pH of the water, slowly releasing food to the plant exactly when it needs it.
So, the suspense is building. We've got a porous mineral sponge, a modified chemical mix, a bacterial compost tea, and a literal live aquatic plant. Which of these completely natural, zero electricity additives actually optimize the harvest and save the Kratky system from its own stagnant water?
Well, let's eliminate the failures first, because the microscopic drama here is actually kind of fascinating. Step 1. Treatment 3. The compost tea. While it's absolutely great in soil, in this stagnant water, the aerobic bacteria from the tea aggressively competed with the plant roots for the already limited oxygen, basically suffocating the basil even faster. Step 2. Treatment 2. The 10% ammonium. See, when plants absorb ammonium, they release hydrogen protons. In a static system without water circulation, these protons just accumulate and highly acidify the root zone, causing toxicity. So, Step 3. Because of these biological and chemical reactions, both the compost tea and the ammonium failed to even beat the standard control system. Ouch.
Section 2. The plot twist. Biooxygenation.
Let's look at the most surprising contender in the entire experiment, treatment 4. This one used a submerged aquatic macrophyte, a plant called Ceratophyllum demersum, commonly known as the foxtail plant. The whole idea was to emulate natural aquatic ecosystems where underwater plants provide oxygen for the environment. And wow, the data here is just jaw-dropping. The aquatic plant successfully acted as a biooxygenator. It boosted the dissolved oxygen in the stagnant water by a massive 41.2% over the control system. Simply by living and photosynthesizing under the water alongside the basal roots, the foxtail plant pumped pure oxygen into the system, completely solving the Kratky method's biggest flaw without a single electrical air pump.
But, every great twist comes with a catch, highlighting the sheer complexity of biology. We have a brilliant success here. The foxtail plant pushed dissolved oxygen levels to a pristine 8.44 milligrams per liter. But we also have a tragedy. The aquatic plant didn't just share oxygen, it also ate the food. It heavily competed with the main basil crop for essential nutrients in the water. So while the basil roots were breathing perfectly, they were ultimately starved. The basil's growth was severely stunted, producing 48% less biomass than our eventual winner.
Section 3. The champion. Treatment 1.
All right, it is time to introduce the undisputed champion of the experiment, the additive that perfectly balanced the chemistry, protected the roots, and optimized the zero-electricity system was treatment 1, the zeolite impregnated with the standard Steiner Universal Nutrient Solution. The data punchline here is absolutely staggering. Treatment 1 achieved a massive 64.32% increase in fresh basal biomass over the control. The plants were taller, they were greener, and they were significantly heavier. It didn't just improve the system, it literally supercharged it.
So what's the exact science behind this victory? How did rocks outperform everything else? Well, the impregnated zeolite perfectly compensated for the lack of electrical water circulation. First off, it acted as a dynamic reservoir, holding on to nutrients and releasing them exactly as the plant needed them, rather than letting them just degrade in the static water. Second, it chemically buffered the pH, preventing the water from becoming too acidic or too alkaline. And because the environment was so stable, the plants increased their root volume by 67.5%. To put that into perspective, that massive root system allowed them to boost their nitrate absorption by 18.4%. The zeolite essentially acted as a chemical battery, powering the plant's growth with zero electricity. And this brings us to why this matters for you, and honestly, for the future of food. This research rigorously validates a low-cost, highly sustainable alternative for urban agriculture. It proves, without a shadow of a doubt, that you do not need expensive pumps, timers, or a massive energy footprint to achieve commercial-level yields. By understanding and leveraging basic chemistry, like our zeolite mineral sponges, we can unlock highly accessible, high-yield urban farming for anyone, anywhere. It's a real game-changer.
I want to tie this rigorous scientific endeavor back to pure human curiosity. In the acknowledgments of his thesis, Ramirez Moreno included this absolutely beautiful quote from Albert Einstein: "Never regard study as an obligation, but as an opportunity to penetrate the beautiful and wonderful world of knowledge." And this experiment is just a perfect testament to that. By looking deeply into the mechanics of water, rocks, and roots, we actually find incredibly elegant solutions to massive global problems.
Which leaves us with one final thought to chew on. The science is proven, the methods are accessible, they're cheap, and they are entirely off the grid. So how will you implement these passive, zero-electricity systems in your own urban environment? Whether it's a balcony, a rooftop, or a community garden, the power to grow sustainably is quite literally in your hands. Thank you for joining me for this explainer, and keep exploring.